f of x equals log to the base e of 3x minus 3x, where x is positive. We want to show that 1/3 comma minus 1 is a local maximum point of f of x. So I've written down f of x again. I've written ln for log to the base e. Now x has to be greater than 0. Why is that? Well, it just means we cannot get log to the base e of a negative value. You know, we can't get, when we get log to the base e of something, this x has to be positive, because e, no matter what power we raise e to, we always get a positive answer. You know, x can't be minus 1. I've explained this in other videos in the algebra section. If, say, x was minus 1, then we'd have e to the power of y equals minus 1. Well, there's no value of y that gives e to the power of y equal to minus 1. E itself is a positive number. E is 2.7. A positive number raised to any number is always positive. So that's all. That's only a small point anyway. Now we want to look at the derivative of this function at a turning point, and the local maximum point is a turning point. The derivative is 0, because at a turning point, whether it's a local max or a local min, the slope, well, the tangent is a horizontal line, which means that its slope is 0. So the slope of this line is the derivative of the function at x, and that must equal 0. I've explained that loads of times before. So the x value of this point is 1/3. So we want to show that the derivative of f at x equals 1/3 is 0. So we need to differentiate this. To differentiate ln of something, we put 1 over the argument. We put 1 over this. You can look that up. So it's 1 over 3x. But then we have to use the chain rule. We have to differentiate 3x to get 3. So we put 1 over 3x multiplied by 3. And these 3's cancel. So we get 1 over x. And when we differentiate minus 3x with respect to x, we get minus 3. If we work out f prime of a third, we have 1 divided by a third. Well, that's the same as 1 multiplied by 3, which is 3. So we get 3 minus 3, which is 0. So that tells us that at x equals 1/3, we have a turning point. But of course, it could be a maximum or a minimum. We don't know that yet. It doesn't necessarily have to be a maximum. It could be some minimum value. As a matter of fact, this point here, 1/3 minus 1, is a point that's below the x-axis. You can see that the y value is negative. So I'm showing here 1/3 minus 1, and it's definitely a turning point, but it could be a local minimum. It could look like this. Well, that's not the best sketch, but like this. That's not very good either, sorry about that. So the derivative is 0. The tangent is horizontal. Or it could be a local maximum. Just to recap on how to actually find turning points, we would have to solve the equation f prime of x equals 0. Well, f prime of x is 1 over x minus 3. We put it equal to 0 and we solve it. So we get 1 over x equals plus 3. Turn both sides upside down. We get x equals 1 over 3. You see there's only one solution. Okay, well that's actually given to us. But the reason I solved this is just to show that there's only one solution, that there's only one turning point. So that could be helpful in drawing the graph. If there's only one turning point, if we know there's only one turning point. You see there's only one solution to this equation here. X equals 1/3. It's not a quadratic equation. If it was quadratic, we would have two solutions. One way to show that this point is a local maximum is to look at the second derivative of the function at x equals 1/3. If the second derivative is less than 0, then the point 1/3 comma minus 1 is a local maximum. So let's go back to the first derivative again. The first derivative was 1 over x minus 3, which can be written as x to the power of minus 1 minus 3. So let's get the second derivative. Differentiating x minus 1 with respect to x, we have minus 1x to the power of minus 1 minus 1, which is minus 2. The derivative of minus 3 is 0. So this is minus 1 over x squared. And if we get the second derivative at x equals 1/3, we get minus 1 over 1/3 squared. Well, 1/3 squared is 1/9, and this is minus 9. Well, the value doesn't matter. What matters is that it's negative. Because it's negative, the second derivative is negative, it means that 1/3 minus 1 is a local maximum. So that's one way to get the local maximum. I explained this in detail in a previous video, why it is that the second derivative is less than 0 at a local max. You can look at that video if you want to see the reasons, but you know, it's well worth remembering anyway. The second derivative is less than 0 for a local max. It's greater than 0 for a local min. Now, another way we could have shown that that 1/3 minus 1 is a local max is to consider values on either side of 1/3. Two values close to 1/3, but on either side of it. We could have picked, say, 0.3, which is less than 1/3. 1/3, remember, is 0.333 recurring, so 0.3 is just to the left of it. And pick a value to the right of it, we could have picked 0.4. 0.4 is greater than 0.3. If we work out f of 0.3, we should get a value that is less than minus 1. If we work out f of 0.4, we should also get a value that is less than minus 1. So because the tangent to the curve at 1/3 minus 1 is a horizontal line, you can see that if f of 0.3 is less than minus 1 and if f of 0.4 is also less than minus 1, then the curve must look like this. So that's another way you could prove that this point is a local max. I've just done the calculations here to show you. If we work out f of 0.3, we actually get minus 1.0053. So we do get a value that's less than minus 1, slightly less than minus 1. If we work out f at 0.4, we get minus 1.02. This is given to 2 decimal places. So again, we get a value that's less than 0.1. So indeed, doing it this way, we can see that we have a local max at x equals 1/3. In part 2, we want to deduce that the graph of f of x does not intersect the x-axis. Well, we have a local max. We know that there's only one turning point. This is it. This turning point is below the x-axis. So it's a turning point that's below the x-axis and it's a local max. So the curve must continue on going down like this, decreasing for values of x less than 1/3 and values of x greater than 1/3. Because if it did not increase, it would have to start increasing and crossing the x-axis. But that can't happen because then we would have a second turning point, and we don't have that. As we saw earlier, there was only one solution to f prime x. F prime of x was 1 over x minus 3. There was only one solution to this equation. The solution was x equals 1/3. So there's only one turning point. So the graph can't turn back again to cross the x-axis. So that means that the graph never crosses the x-axis. So it must continue on like this here.